Okay. In previous class, we have already studied that is the what about the introductory part of the mass transfer operation and the diffusion process. Okay. We will continue here for this class some basic information that thing is already known to all of you. That is, we are starting this subtopic that is the molecular mass transfer mainly. What we are saying is the number of molecules of each species present per unit volume. All of you know that that is nothing but this your concentration mainly. Or we can say that molar concentration of species I, if we consider one particular species, that we can say that Ci is equal to number of moles of I present per unit volume. That is nothing but the your molar concentration, and unit should be in SI system that kilomole per meter cube. Now mass concentration. What is mass concentration? Mass of I or individual species I per unit volume. That is nothing but the mass concentration. And all of you know that this, if we talk about the mass concentration or we can say total mass concentration, that is nothing but the density only. Okay, that is the rho y is equal to mass of I per unit volume, and the unit is kg per meter cube. Now we will apply this ideal gas law PV is equal to nRT. From here, simplify all these things and we can write that one another part, that is the mass fraction. What is mass fraction mainly? We are representing in Wi, that is nothing but the rho y by rho. Your rho I is the individual component mass concentration divided by rho, that is nothing but the total mass concentration, or we are getting this mass fraction of species. And same way we are writing here, that is the mole fraction of species xi, small xi is equal to Ci by C. Now if we are considering this n number of species in a solution we have, then we can write that these four small and very useful equation, that is nothing but the summation of I is equal to 1 to n, rho y is equal to rho, that is nothing but the total density of the system or solution we are saying, and summation of I is equal to 1 to n, Ci is equal to C, total concentration of the solution, and the mass fraction, that is the summation of I is equal to 1 to n, Wi is equal to nothing but the obviously 1 if it is a mass fraction. Same way for the mole fraction, the summation of I is equal to 1 to n, xi is equal to 1. And this terminology mainly we are using here in your mass transfer operation. This small xi representation mainly we will use for the term mainly liquid phase and if it is a solid phase. But if it is a gaseous phase, we are using small y. That means summation of I is equal to 1 to n, yi is equal to 1. That is the mole fraction of species in a gaseous phase mainly. Okay. Now if we apply this, our ideal gas law, we can easily write that the rho A is equal to Ma by V as well as Ca is equal to Na by V, your number of moles divided by volume. Just apply the ideal gas law equation, you can simply write that Ca is equal to Pa by RT. Your Pa is nothing but the partial pressure of the species A. Okay. Now again we can simplify that Xa is equal to Ca by C, just using this term and apply this ideal gas law. Again we can write that for gaseous phase Ya is equal to Pa by P, nothing but the partial pressure of species A divided by the total pressure of the system in a gaseous phase. Okay. Now another two term is there, that is nothing but we are saying say mass average velocity and molar average velocity. The molecular transfer is happening or transport is happening, and for that one we are saying say velocity of a particular species is relative to the mass average or molar average is the diffusion velocity. And when we are saying it's a mass average velocity, the representation is small u is equal to, you can check that, summation of I is equal to 1 to n rho y uy divided by summation of I is equal to 1 to n rho y. Here, your rho y is equal to mass concentration of individual species in a solution. Ey is nothing but your linear velocity or simply velocity, and rho y is your mass concentration. And you can see that the denominator will become the rho only, total mass concentration or simply density of the solution or density of the system, whatever the things we are considering, and we can get that finally summation of I is equal to 1 to n rho y uy by rho. In same way, for the molar average velocity, the representation is capital U, and we are saying that it is nothing but the summation of I is equal to 1 to n Ci Ey by summation of I is equal to 1 to n Ci. Here your summation of I is equal to 1 to n Ci is nothing but the total concentration of the solution. We can write that on 1 by C into summation of I is equal to 1 to n Ci Ey. Those things is already known to you. Just for the recording purpose, we are presenting here. Now, all of you know that term flux. Okay, mass flux and molar flux. What is this flux mainly? The term flux means the net rate at which a species in a solution passes through a unit area. Okay, we have already studied those two transfer process or operation, momentum flux as well as your heat flux. Okay, that is nothing but the rate of heat transfer per unit area. Same way for this mass transfer or mass flux or molar flux, what we are saying is a rate of mass transfer per unit area. If it is a mass flux, what should be the unit? That is the kg per meter square per second. Okay, kg per second is the rate of transfer per unit area. It will convert to a flux. Same way for the molar flux, kilomole per second, that is the rate of molar or rate of transfer of moles, that is the kilomole per second per unit area. Then you will get the unit kilomole per meter square per second, that is the mass flux and molar flux. Okay, now the governing equation or basic law of mass transfer, that is, we are saying it's a fixed law of diffusion. Fixed law of diffusion. What is this fixed law? Mainly, we are saying that is nothing but the linear relation between the rate of diffusion of chemical species and the concentration gradient of the species. Here, your rate of diffusion, we are representing this term JA proportional to the dCA by dZ, that is nothing but the concentration gradient, change in concentration per unit or per length, whatever the some distance. That is, now if we simplify this, we are getting this equation is JA is equal to minus DAB dCA by dZ. Here, your DAB, this term represent the diffusivity. Okay, that is the diffusivity or molecular diffusivity, DAB. Now you can recall that for our heat transfer, the equation was same or alike. You can say that is the rate of heat transfer or rate of transfer of heat, capital Q is equal to minus K into A into dt by dx. Your K is the thermal conductivity, A is the cross-sectional area and mainly heat transfer area, and dt by dx, temperature gradient, difference in temperature per length. Okay, there also one negative sign was there. Here also one negative sign is there. Same for if we consider the momentum flux also. Momentum transfer, you can recall that is nothing but the tau is equal to minus mu du by dx. Here, why this negative term is there mainly? Here, you can say that always the transfer or transport is happening towards the negative direction or from higher to lower. Okay, towards the negative direction. Now, that part mainly, that is the differential part dCA by dZ, this term will become negative. Okay, but this rate of transfer, or if we say only that is for this mass transfer, we are saying it is a positive quantity. your rate of heat transfer also, that is a positive quantity. The rate of mass transfer, that is also a positive quantity. For making the consistency of this equation, we are putting one negative sign, and that is the significance of the putting one negative sign for all this similar kind of whatever the transport basic law or equation value. Here, the DAV we are saying, and it is a diffusivity, and the unit is distance square per time. In SI system, normally we are saying meter square per second. The J is the molar flux of component A in the Z direction in kilomole A per meter square per second. Okay, and Z is nothing but the distance of diffusion path we can say, and Ca is the concentration of A in kilomole per meter cube, that is the concentration unit. Then we are getting our fixed law of diffusion or basic equation for the mass transfer, that is the J is equal to minus dAV dCA by dZ. Now, according to Fick's law, the molecular diffusion, the molar flux of a species relative to an observer moving with molar average velocity is proportional to the concentration gradient in a certain direction. Okay, here, because of this term, the species relative to an observer moving with molar average velocity. Here, one example we are saying that perfume example mainly. Now, how the diffusion is varies mainly, we can say that velocity, species relative to an observer moving with molar average velocity. I have already shown you two average velocity is there. One is the mass average velocity and molar average velocity. Here, one term is there, we are saying it's a frame of reference. Okay. Now, if the object or your observer both in a static mode, that time we can say, or we can find out the rate of diffusion. Another frame is there. Your observer is moving with a molar average velocity. That time also we can get the diffusion or rate of diffusion. And another kind or another case is your observer is moving with molar average velocity. One is the static, mainly your observer is static, and the static, another way you can say that your object is also moving and your observer is also moving in a direction in a same velocity. This is also one case. Now, here we are saying Fick's law, the molecular diffusion, the molar flux of a species, means we can define the flux in three different frame of reference mainly. One is the static mode, another one is the your observer is moving with mass average velocity, the observer is moving with molar average velocity. In the three particular case, we can find out the flux mainly. According to the Fick's law, the diffusion flux is proportional to the negative gradient of the concentrations. Just whatever previously I have explained. But flux, it is a mass flux mainly J is a positive quantity. That's why how we are getting this? Putting one negative sign, and it is a make the consistency of the equation. The diffusivity or diffusion coefficient, we can say DAV is nothing but the diffusivity or diffusion coefficient is a proportionality constant and is defined as the ratio of molar flux to its concentration gradient. From that particular equation, you can easily find out that. Okay. The several factors affect the rate of diffusion that I have already said. That is the time, temperature, as well as the mass of the solute, the solvent density, and the distance traveled. All those things are affecting the rate of diffusion. J is the diffusion flux, of which the dimension is amount of substance per unit area per unit time. That is already explained. Okay. From there we are getting that mole per second per meter square. Okay. Mole per second is the rate, per unit area is the flux. Okay. J measures the amount of substance that will flow through a unit area during a unit time interval. That is the flux. Now, the diffusion can occur in two ways. I have that also explained. One is the molecular diffusion, another one is the convective diffusion. In molecular diffusion, the driving force is the concentration difference. If we consider the convective diffusion, there is the bulk velocity of particles and the medium also it will affect. Okay. Now, two terms mainly we will use here. One is the molecular diffusion flux representing by J suffix capital A. Now, another one is the total flux when we are considering the convective flux mainly. If the person is moving and the observer is stationary, then the diffusion of molecules is observed having both the effects of molecular flux as well as your convective flux. Okay. When we are saying that one, if the person is moving and the observer is stationary, what about in person? We put perfume. That person is moving. I am the observer. I am in a stationary mode. That kind or that at that instant of time, what should be the flux? That is nothing but the total flux. That time your molecular flux as well as your convective flux both will be happening. Okay. Now, if we merely summarize this, we can say that that is the summary of three transport process. Three transport process mainly, that is the momentum transfer, heat transfer and mass transfer. That I have already said. Now, I have given you one proper tabular example mainly, that is the in momentum transfer, the driving force is nothing but your velocity gradient and the transport property is nothing but the viscosity or kinematic viscosity. Okay, and this corresponding law is we are saying say Newton's law of viscosity. Tau is equal to minus mu du by dx. For heat transfer, the driving force is temperature gradient. The transport property is thermal conductivity, or we are saying it's a thermal diffusivity. And the corresponding law or governing law is nothing but the Fourier's law. Q is equal to minus Ka dt by dx. Here, mass transfer, the driving force is concentration gradient or chemical potential, and the transport property is mass diffusivity, that is the DAB or diffusivity. The governing basic law is nothing but a fixed law of diffusion. J is equal to minus DAB dCA by dx. Now, we can find out that the molar flux of A in a binary mixture of A and B. We are considering the mixture of two component A and B, where it's a binary mixture, and we want to find out in that particular mixture the flux or molar flux of A, and the presentation is nothing but the your NA. Okay, how those things we have already know that is the molar average velocity, capital U representation. If it is a two component system, we can easily write that molar average velocity capital U is equal to 1 by C Na plus Nb. And again, we can write that for particular species A and B, Na is equal to Na individually Ca into small ua and Nb is equal to Cb into small ub. Now we are just correlating. We know that from the fixed law, J is equal to minus dIb dCA by dz, and again we know your J is nothing but the Ca into ua minus capital U, that is the molar average velocity. If we simplify it, and we will get that Ca is nothing but the Na, and again in terms of capital U we can put that is the value, and if we simplify that we will get that Na minus Ca by C into Na plus Nb. From there you can write that Na is equal to, just take in that side, minus Ca by C will be positive, Ca by C Na plus Nb minus dAb into dCA by dz. Now we could say that the molar flux of A in a binary mixture of A and B with respect to a stationary observer. I said in stationary observer, two component is there. One is the your molecular diffusion, another one is the your convective diffusion. That is the molecular diffusion part and that is the convective diffusion part. Okay. The flux Na consists of two terms, bulk flow term, that is the convective term, Ca by C Na plus Nb, and the molecular diffusion term minus DAB dCA by dZ. From there, we will get this our equation, that is nothing but the flux, molar flux of A, Na is equal to Ca by C into Na plus Nb minus DAB into dCA by dZ. Now, we can write that this Na is equal to Ja also. When we are writing that one? When we are considering that the concentration of A in a mixture of A and B, considering that is the perfume example, your ambient air we are saying it's a B and your perfume molecule is A. If the perfume molecule concentration is very small compared to the ambient air, we can say that the perfume is very diluted in air molecule. In that case, we can say it's a dilute solution. The contribution of the bulk flow term becomes very small. In that particular case, when we are considering it as a dilute solution, we can write that Na is equal to J is equal to minus DAB into dCA by dZ. Okay. Now, that for this term concentration we are using for the liquid phase, and we can use this for this gaseous phase using the ideal gas law. Simply we can write that I have already shown previously that Ca is equal to Pa by RT, partial pressure of A component, and capital C is equal to P by RT, total pressure by R and T, that is the universal gas constant and absolute temperature. Now, if I substitute this value in our previous equation of flux Na, just you will get that Na is equal to Pa by P into Na plus Nb minus in place of this whatever the C and C, we will get that dAB by RT dPA by dZ. Then our representation in terms of partial pressure and total pressure for the gaseous phase or gaseous mixture. Okay. Again we can use this in terms of mole fraction also. The equation will become Na is equal to Na plus Nb into Ya. Ya is nothing but the gas phase mole fraction of Ya minus C into dAB into dYA by dZ. These are the expression for the molar flux of A in a binary mixture of A and B for the liquid phase or liquid solution as well as gaseous solution or gaseous mixture. Okay. Thank you.